Yeah, no, yeah, but in far as the computer is concerned,
No, I know.
Try for the second one.
yeah.
If I can, no, you continue this one. I'll try just.
Um, installing driver's software. Hang on. Maybe that's the problem.
Yeah, you are using your laptop? I left mine in the hotel.
Still installing driver's software.
I think.
Yeah. It says now it's ready to use,
Okay.
but it doesn't show, so hang on, let's just try to remove it then. Okay, we understand that. Now explain to me
Ah,
why.
here it is.
Here it is. Fine. Finally. Hang on a sec.
1 second.
There?
Maybe we make open.
This is what it is?
I hope so.
Here, this is your,
With mine.
where's your talk?
It's Washington,
Oh, okay.
but you can.
Modify. Oh, long.
Is it an old computer, this one?
I don't know. Let's remove. Oh, you can eject. Okay. All right. Who's next? Yeah, it's not my laptop. I don't know what the problem is. Yeah.
20 minutes.
Yeah, it should be okay. But you can try, sure, yeah. I'm sorry?
A portable
Microphone?
mic. This one, yeah.
I believe so, yeah.
There's
Yeah,
several.
yeah, yeah. So, Roman, which of you have many? Which one is it? This one?
I think the safest is the latest.
What? Oh, PDF.
Yeah, PDF.
Yeah. I just you don't want to use PowerPoint. Okay.
It isn't PowerPoint.
Yeah, I understand. Yeah. Okay. And then, all right. That's okay. Oh, it's already in the memory stick?
Yeah.
Okay.
Yeah, we will share the flash.
Okay, well, hang on. That I didn't see. Oh, here we go. One, Shijun?
Yeah.
Oh, he has one also?
You switch my microphone, the slides.
Oh, I guess if you, I mean here you just do here, I guess.
I stand here.
Oh, I'm sorry. You mean to what is it? Function. Oh, you unplugged it. Oh, I see. There we go.
And let's say full screen. No. Control con. Window. Screen. Control L. And then
So
I
it's
use
control what?
Control L. And I don't need this. This is
Yes,
enough.
but if you walk away, it's because it's being recorded. So yes, you can use this. Other people have. Whatever you're comfortable with.
So
It's
they,
your choice.
okay, they work simultaneously.
They should work, yeah. So if you get them to close, you might have some feedback.
Okay,
So
let me try.
this one is now on. Hello?
No,
Was
this,
on.
this should be
Now it's on. Hello?
Wow.
1, 2, 3.
okay.
Okay. All right.
Okay.
Yep. Okay. All right. Now I'm going to put on another one. You want to test something? All right. Yes. There may be some other adapters. I don't know, like this one here. Is that okay? All right. I'd like to make just a quick reminder, announcement that I made earlier, actually. For those of you who have posters, please put them up now. There's also been a misunderstanding. The dimensions of the posters were supposed to be limited. So on one poster board, you have room for 2 posters. So if you're in the middle of it, you should move it to the side. Okay? Also, the numbers were random. We didn't ask for numbers. We've taken the numbers down. You can put your poster anywhere. But if you're taking up too much room, just as a courtesy, please move your poster to one side or the other. All right, so Andy Rapp is the chair for this session. Andy?
All right, good morning. It's a pleasure to welcome you back to the second session, and I'm happy to call for the first talk, What Makes the Difference in Perovskite Oxides, by Annette Busmanholder. Hello. Hello?
Okay, good morning, everybody, and thanks to the organizers for keeping up this conference, running this conference. It's amazing. It's now, I think, about 28 years, 28th time, or how often is it? It's true, yeah? Typically, I end up in a snowstorm coming to these conferences, and we don't know what's going on until Thursday or Wednesday, so eventually it ends the same as always. So I'm talking today about perovskite oxides, and of course everybody is familiar with these types of crystals and systems. But the question still remains, what makes the difference? Why are some of these oxides ferroelectric? Why are others not? Why do they undergo rotational instabilities? Why don't others do that? And so what I did, I started from a very systematic approach. So I said, I will just keep the BO3 unit intact and compare by replacing the A side, the dynamics of these systems to each other. On the other hand, if I find time, I will shortly talk about the reverse process. I keep the A side the same and change the B side. So this should tell you or give you some information what is going on in these perovskite oxides. So this is what I just said. And typically what you do, so there are many approaches like that, but the simplest one is based on Goldstone, Goodenough, Glaser, and all these people, that they say the tolerance factor is a decisive quantity to differentiate between the ground state properties. The tolerance factor is familiar to all of you, and in its most simple form, it says if the tolerance factor is less or equal to 1, the system should be stable and not undergo a ferroelectric instability. However, if the tolerance factor is bigger than 1, it is expected that the system undergoes a polar instability. But this is just not true in these compounds, as you can see here. Only barium titanate fulfills this condition, while lead titanate is ferroelectric and T is smaller than 1, and these two are not ferroelectric and have T approximately equal to 1. So this is an approach to try to figure out what is the relevant quantity in deciding about the ground state properties. This is just a very, very short summary of the properties of the compounds I'm talking about. So barium titanate is, as everybody knows, is a ferroelectric below 400 K approximately. It has long been debated to be either order disorder or displacive ferroelectric because there's a soft mode, a transverse optic soft mode, but simultaneously local dynamics shows that there must be some order disorder component. And there were recently a couple of papers which showed that you have a coexistence of order disorder and displacive character. PTO has long been believed to be the classical soft mode-driven displacive ferroelectric, but also again recently XFs and SANES results, NMR and all these local tools showed that there's also an order disorder component in this crystal glass. CTO is the eponym for perovskites. It was discovered long time ago and by somebody, this doesn't work properly, not by Perovsky, but Perovsky made it famous, but by this German mineralogist Gustav Rose. And this is, of course, intensely investigated, undergoes various phase transitions, but never turns ferroelectric. Then I go to further perovskites, titanates. Strontium titanate, everybody knows, is, I think, the best investigated perovskite at all. It is well known for its interfacial properties, for superconductivity as a layered material, so it is well investigated. And even nowadays, if you look up the citation of strontium titanate, you find at least something like 10 papers per week on this compound in all its different modifications. Europium titanate is antiferromagnetic below 5.5 Kelvin. This is known since about 60 years almost. And it was supposed to be very boring until we found out that until the group of Stanislav Kamba and the Czech group found out that a dielectric anomaly with a drop of 7% it can be related to a soft mode. And from then on, it was in the intense research due to the fact that it could be a low-temperature multiferroic. But this is not the issue. So I go through this only very quickly because there are too many papers on these perovskites, so I really cannot cite everybody and all the papers, but I'll just give you a short outlook of the papers. So first thing is, of course, to look at the electronic structure of these compounds and compare them to each other to figure out is there a signature in the electronic structure which can differentiate between all these 5 different titanates. And if you look at it in detail, then you see more or less they all have the same features. Oh, yeah. You have the p-band being the valence band being dominated by p states, oxygen p states in all these compounds. There's an admixture in lead titanate from the lead s bands in the valence band, and the conduction band is dominated by the d electrons. The bands, the only exception is in europium titanate. You have a very, very localized band from the F electrons sitting in the band gap. If you look at the pure band gaps in all these 5 compounds, they are more or less the same. There's something in between 3 and 5 EV, so there's not something which would tell you this compound is a ferroelectric, the other one is not a ferroelectric, if you look at these band structures. So we looked at another series of compounds just to compare these two to each other. That is what I said in the beginning. We exchanged the B-side ions, so the transition metal, to figure out whether this one is a driving force. So we kept the A side intact and modified the B side, and then compared these 2 series to each other. We took the lead transition metal oxides, but you can do the same for the series of, for instance, barium, titanate, hafnate, and zirconate, europium titanate, zirconate, hafnate, etc. So the trends in all these families are the same, and you can somehow generalize what is coming out for this series. So These are well known, so you have in all these compounds, you have also transitions from cubic to lower symmetry. Lead titanite is the only one which is ferroelectric at rather high temperature. Lead zirconite undergoes two transitions, which are to an antiferroelectric state rather similar to lead hafnate, whereas lead zirconite, one transition is a little hidden below the other one. I think we will hear about this later on. So these transitions are almost on the same order of magnitude and all are going to a polar structure. So again, common are the features that the B ion is left intact, and as I said, the B ion itself doesn't change the transition series in these compounds. So I come to the band structure. Here, lead titanite is compared to lead zirconate, and here you have two different methods of evaluating the gaps in the hafnate. But again, what is obvious in all these series is that the valence band is dominated by the p states of oxygens with admixture of the s states of lead. And again, the conduction band is almost exclusively made up of transition metal D states. The band gap, and this holds for all these compounds where you keep the A site intact, the band gap is systematically growing if you replace titanium by zirconium by hafnium. But this is, you can follow it through all 4 or 3 series which are existent, but this is due just to the fact that you have a bigger volume and the D states are more expanded if you go to the higher homologs. So again, from this data, this is reference to the work, so it's really a lot of work being done on all these compounds. So what we did from the very beginning, we calculated the double wear potential in the titanium or transition metal oxygen interaction, the PD hybridization effect. And what is a self-consistent calculation, so it is parameter free. And what is entering in the calculation is this average distance titanium oxygen in all these compounds. What is now very evident from the very beginning, this is europium titanate. It has a very narrow potential, rather deep, and so there is almost no room for the transition, for the PD hybridization to become effective. If you go to the next compound, this is calcium titanate, you see it's getting broader already. So this means you have a trend to delocalize and hybridize PD states of oxygen and then transition metal. And with respect to strontium titanate, it's getting even broader. But they're still shallow, so this indicates that you are far away from a real ferroelectric or polar instability. Now, if you turn to lead, this is the blue line, you see it's still rather small, so not far extended, but I have to add here that in lead titanate you have to take into account the lead ion polarizability, so that the potential differs caused by this lead ion polarizability. Now we come to barium titanate. This is this broad potential, so very broad and very steep, and what came out from the calculation is that barium titanate can as well be described by this dashed green line here, because it has a first order transition. So this shows up in the fact that the dynamics can be modeled by 2 kinds of potential. But in the following, I just take this broad double wear potential because it doesn't make a big difference for the dynamical properties. But you have to keep in mind that the transition in barium titanate is first order, and this is reflected in this dashed potential shown here. So the first thing which we did is to calculate self-consistently the soft optic mode, which is common to all these 5 compounds. And what people easily and often overlook is that the soft optic mode is coupled to a soft transverse acoustic mode at the zone boundary. So if you look in experiments, then you see that the optic mode, the polar ferroelectric mode, causes an acoustic mode to soften simultaneously, but much less than the transverse optic mode. And so I compare here the 2 modes. So this is lead titanate, The full symbols refer to the optic mode and the open ones to the acoustic mode. So you see that this mode drives also some mode which is caused by rotational instability. This is more obvious in barium titanate where you have a mode crossing. So you see that first the acoustic mode is much softer than the optic one. Then there's a mode crossing, and this has consequences for the precursor dynamics and the formation of polar nanodomains. Now these two can be compared much more easily because they are all incipient ferroelectrics and they all have a soft mode. But what is obvious from the very beginning is strontium titanate tries to become a ferroelectric, as everybody knows, in the vicinity of 20 Kelvin, but then quantum fluctuations stop it from softening completely. Now looking at calcium titanate, it has the same tendency, but if you extrapolate the optic mode to 0, you end up at minus 40 K. So this means the system is further away from any ferroelectric properties. And now I come to europium titanate, which is the blue lines, and you see it does the same as strontium titanate, calcium, and calcium titanate, but the soft mode stops at around 6 MeV, 6 terahertz squared, the soft mode squared, and it cannot go to 0 at any finite temperature. So from this behavior, this has been called quantum paraelectric. I would say this is not a quantum paraelectric because there are no quantum fluctuations to stop it from softening. It would in no case go soft at a finite temperature. And the same holds for europium titanate. What is also clear from this that you have again this crossing of optic and acoustic mode as a function of temperature. So this might be the origin, especially in europium titanate, why your group has seen this extra mode, you call it extra mode in the dispersion, which shows up below 200 approximately, as far as I remember. So this means that you have this mode goes back to the zone center below the structure phase transition. So you might observe an extra optic mode in the dispersion of europium titanate. Now I come to the dispersion of all these compounds, and you see striking differences in these dispersions. So this is lead titanate. I put in some experimental points, and you see the softening of the optic mode and the simultaneous one of the acoustic mode, which I just plotted before in the slide before. What is really striking is lead barium titanate. You see that it is almost dispersion-free, the optic mode at high temperature, and only gains dispersion if you go to lower temperature. Strontium titanate looks well behaved, the same as calcium titanate, and what is different again is europium titanate. Now I draw these red circles into the dispersion because I wanted to attract your attention to the fact that optic and acoustic mode are interacting with each other at low Q values. So you see here directly, if you look at the open squares, that this mode gets affected by the optic mode. This means you get a softening at finite Q, which tells you that you have a softening on the dimension of a couple of lattice constants. So this could give rise to polar nanodomain formation or elastic anomalies. If you look at barium titanate, then you see here is no something like precursor dynamics because there's no interaction with the acoustic mode. Only if you come close to the phase transition temperature, then you can imagine that you have polar nanodomains or elastic nanodomains coming into the play. In strontium titanate, it's very much like in lead titanate. There's easily the possibility for interactions between the two modes, which is less given in calcium titanate and absent in europium titanate. So if you look at the elastic constants of these systems, you can immediately draw conclusions about the elastic constants because this must be a very hard compound, very stiff. And this has been also seen experimentally because below the structure phase transition, you should see the domain formation, and these are not easily movable, so they're very hard. And here you have the same behavior. Again, there's almost no interaction, the system is very hard, whereas these two others show different behavior. in order to look at the local dynamics. 2 minutes, okay. So we extracted from this something like elastic polar and polar nanodomains by looking at the interaction at small Q values and evaluating this as a function of temperature. So you see europium titanate is anomalous at the zone boundary because you have the spin-spin interaction for the antiferromagnetic ground state. So this is more or less very boring. If you go to barium titanate, you see the elastic anomalies are going to zero, to the long wavelength limit, so it deforms indeed, so, which is obvious from this figure. Calcium titanate remains on a long wavelength limit, but it does not show a homogeneous state. Lead titanate also goes to a homogeneous state, whereas strontium titanate remains in this clustered state. And here's the volume fraction, and you see it's diverging for lead titanate. For strontium titanate not, it remains finite if you go to T equals 0, but it's also diverging for barium titanate, whereas these two other compounds are more or less rather boring in their dynamical behavior. So we did the same for polar nanodomains, and Q actually tells you about the length scales of these nanodomains, and again, europium titanate is at its own boundary, so each second unit cell is affected by polar distortions, but it is not effective if you look at the volume fraction for these distortions. Calcium titanate is the same, is also rather boring and remains in a clustered state, and the same holds for strontium titanate. You see the tendency to form a homogeneous state, but it remains in an incomplete polar state embedded in a paraelectric matrix. This is opposed to barium titanate and lead titanate in accordance with the experimental data. And here's again the volume fraction, which tells you the same as on this side, where we have the length scale as a function of temperature. We calculated the dielectric response as a function of temperature and frequency. You see this here. I will just summarize this data with this one transparency. So you see here the damping as a function of temperature for the 5 compounds. In agreement with experimental data, the damping in lead titanate grows when approaching the phase transition temperature. Europium titanate has an almost temperature-independent damping, whereas these two show or is close to the other 4 compounds. So this is the exception, which tells you about the first-order nature of the phase transition. Then we come to the oscillator strength, which is increasing with decreasing temperature, not for barium titanate and europium titanate. And here's the soft mode frequency as a function of temperature, and you see these 3 extrapolate to 0 or to negative, respectively close to 0 temperatures, whereas these go to 0 at the phase transition temperature. I come to a final, yeah? Okay, so I cannot. That's, no more. Yeah. So is it already 20 minutes? Oh, you are very strict in time. So just to conclude, it is obvious that the A site in the perovskite plays a fundamental role for the dynamics and also for the phase transition, just opposite to what one would expect if you know that PD hybridization effects are driving a polar instability. Thank you for your attention.
Okay, can the next speaker come right up?
Thinking about this in terms of the hybridization of the acoustic mode and the optical mode, when you're thinking about the oxygen 18 dope strontium titanate and the potential polar nanoregion formation there, would you expect the isotopic doping to shift the acoustic and the optical mode differently to cause a crossing, or is there? Yeah, so in the isotopically doped strontium titanate, the 018 doped strontium titanate, for example, how would that affect these?
Oh, this does not affect the dependence of the two modes on each other. What you see, however, is that the optic mode goes soft indeed, but it does not play a role for the temperature dependencies of the two modes, so they remain the same. But strontium titanate, the oxygen isotope replaced strontium titanate, is also not a ferroelectric in the sense that it is truly ferroelectric, but it's something like also very inhomogeneous state.
Okay. Well, let's thank Annette again. Okay, the next talk is the link between Goldschmidt tolerance factor. Your updates are ready. Lattice instability type. And diffuse scattering character in perovskite crystals and films. Roman Burkowski. Okay, so I'll tell you, at 15 minutes, I'll go like this, which means it's fast.
Thank you. Dear colleagues, thank you very much for the opportunity to see you here and for the opportunity to be here. Very nice city, very interesting. I came from Peter the Great St. Petersburg University, technical. This university is quite beautiful. It is in St. Petersburg under snow, close to the night, and here we make our science and education. I should thank Annette very much for allocating attention to the Goldschmidt tolerance factor and to the instabilities in crystals, because I will speak about the same things in some sense, but from the different perspective. Lattice instability, what it is. One can separate it into two questions. One question is which atoms should shift, and the other is what is the pattern in space of these shifts. Which atoms should shift? And here Goldschmidt tolerance factor comes into the play. Formally, it tells whether there is some free space for some particular ions. If it is less than 1, there is some free space for the A ion and for oxygen to moving towards A ion. If it is more than 1, B ion is, let's say, almost free there. We know it is not strictly the case, but formally there is free space for him. And for oxygen, there is also an opportunity to move towards B ion. I should draw your attention, it is not strictly the projection from of the unit cell, it is, let's say, artistic description, because if that would be strictly the projection, I should try plotting one atom after the other. It is more difficult to appreciate. But I will use these diagrams throughout the talk. Tolerance factor is depicted in on the bottom. And the second question is more difficult to answer. Once we know that either B or I cations do shift due to tolerance factor, we don't know whether it will be ferroelectric instability, antiferroelectric instability, or perhaps incommensurate instability. Goldschmidt tolerance factor doesn't say formally anything about it. Before trying to address this question, we should recall what the instability is and how do we understand why does it occur. This is the paper of Anderson, soft mode paper, the very famous one. And he says there is a stiffness, wave vector dependence of the stiffness. And there are short-range forces and Coulomb forces, which are competing. And the instability occurs as a result of a delicate balance between them. And after 60 years, we still think this way, as it is evident from the papers that we publish. And Anderson says, okay, we add a Lorentz correction to the short-range forces, and this renormalizes the stiffness down, and we have instability at the zone center. And this renormalization should look like this. But then we should only have ferroelectric instabilities. We shouldn't have antiferroelectric or incommensurate. But let's say the core of this study that I present is that it is not necessarily the case. If we look more carefully, when we consider all the atoms in the perovskite unit cell, the Lorentz correction becomes different. This is, let's say, I should go back again to Washington. Here are some Mason lodges, and this is triangle is from that. So we want to understand physics, and we should bring up the model that gives us the Lorentz correction. Due to this Lorentz correction, it is everything linked to the experiments, to lattice instabilities that we observe, or to diffuse scattering that we measure. On the other hand, the model has parameters, and these parameters are polarizabilities. When we compute Lorentz correction, it should be like that in the simplest case. And then these parameters we can link to tolerance factor, to electronic polarizabilities, and in the end to the values that are tabulated in the handbooks. Let's say ionic radii and polarizabilities. But because the model is very simple, and we work with a very simple one, it is possible to look inside and get the answers how it works. Why? This is the model. If we look at the dashed line, it connects the external field, which is applied to the crystal, and to the dipoles that live inside. This is similar to the model of Slater, and this is a generalization of that model to finite wave vectors, to homogeneous solutions. And what connects the field and the dipoles is the stiffness. Stiffness is linear in these two variables. But the whole situation is more complex because we have a feedback on the right. Dipoles create fields on them. So the lattice creates the fields on itself. And this is called exciting field, is due to eval this name. And this exciting field, it sums up with the external field and the total field via individual polarizabilities of the cells, of the sites in the cell, makes the resulting dipole pattern. So the idea is to solve this model, to vary polarizabilities, and to look what emerges from that. This is shortly how it is everything defined. It is very similar to lattice dynamical models, like shell model. The dipoles in the wave vector space, they are defined by 15 elements vectors enumerating the sides of the lattice plus Cartesian coordinates. And the stiffness matrix should become 15 by 15 matrix that we can analyze to find the eigenvalues, eigenvectors, and so on. The exciting field is calculated exactly as it is for shell model. So I just skip this slide. It is a summation in real space and reciprocal space. It's easy to find in the textbooks. And then, by using simple linear relations, we can find the stiffness matrix. And this stiffness matrix is composed from two contributions. One is polarizabilities. These are model parameters. And these are Coulomb coefficients that are not variables, that are defined by the geometry of perovskite. How it looks like. On the left, you see the picture of Anderson. On the right, it is the picture calculated by the model. And if you cross it, if you sect it, it is basically the same as on the left. But here it is landscape in 2 dimensions. And this is basically the lowest eigenvalue. So when this eigenvalue becomes 0, you apply 0 field, and you obtain finite dipole pattern. So this is lattice instability. So when we want to understand the instabilities, we look when we have zeros, when with the surface touches the 0 plane. And here is a little bit of jump. but we do that. This jump is we already have two stiffness landscapes. Let's take them as they are, and later we understand what is the mechanics behind them. First type is with low stiffness in the high symmetry reciprocal space planes. And this is highly similar, if not to say really identical, to the first principles results of Krakauer and Yu. Here it is the frequency of the lowest energy phonon in sodium niobate. And the same picture we envisage in barium titanate. So we should, let's say, call this as a barium titanate-like picture. Another landscape is with the stiffness valleys along 110 directions. And this highly resembles what we see on the experiment in lead zirconate. If we look deeper, it is still consistent with these assignments. Green is the labeling in quotes of these cases. In barium titanate case, the eigenvector is this chain motion. Let's say people say about chain motion, chain disorder. When a BO chain moves as a whole, and the motion of these chains is independent from each other, and from this stems this wave vector independence along the valleys. And for lead zirconate case, the motion is transverse lead waves plus the waves that are similar to the antiphase rotations or tilts of oxygen octahedra. This is similar to what first principles calculations suggest. And here comes something like a revelation about which parameters give the solutions. On top, there are polarizabilities, schematic depiction of polarizabilities. The bigger is the circle, the bigger is polarizability of the corresponding lattice side. On the left, for the case of barium titanate, there is large polarizability of B-ion. And the polarizability of oxygen is similar to baguette. It is towards B-ion. And this is what one should expect from tolerance factor consideration, because these directions are the ones where the atoms are free to move. Or perhaps, if you see further, for example, there is opportunity for the electron clouds of oxygen to redistribute inside the so-called free space. This is a matter of imagination. In lead zirconate case, the polarizability of the B-ion is completely suppressed. You see this very small circle. But the polarizability of A-ion is very large. And the polarizability of oxygen is like pancake. So it easily polarizes towards lead. So it is very intuitive that these sets of polarizabilities are arising with these conditions of tolerance factor. So it seems the model just follows the intuition. Interesting thing happens when we vary the anisotropy of the oxygen polarizability. Let's say more pancake-like or more spherical. And by varying that, we vary the level of anisotropy of the stiffness landscape. And if it becomes very anisotropic, that polarizability of oxygen, we obtain incommensurate minimum at the sigma direction. And we made a systematic study of the position of the minimum as a function of axial and equatorial polarizability components of oxygen, and found that every position of the minimum is accessible in principle. But in fact, it seems that the real crystals have their polarizabilities somewhere there around the crystal, around the circle. This is, let's say, how tolerance factor is linked to the position of the stiffness minimum. It is linked via oxygen polarizability anisotropy. In the experiments, we are interested not only in the lattice instabilities, but also in the distributions of diffuse scattering. It is a direct way of probing susceptibility at finite wave vectors, or stiffness. In principle, stiffness is how hard is your soft mode. And this is the comparison of the calculations of diffuse scattering with what is measured experimentally. On the top you see shining diffuse planes of sodium niobate. It is roughly the same as calculation gives. When the polarizability of oxygen is nearly isotropic, the second row, there is no special anisotropy also in the stiffness landscape. And this is something that we see in lead titanate, as Chapman et al. Report. With lead zirconate, there is strong anisotropy. It looks like butterflies, and it is similar to what we see in relaxers. And it is consistent with the experiments of Tagantsov and co-authors. And under pressure, we did also measurements of diffuse scattering, and we have registered these maxima of diffuse scattering intensity, and they are easily reproduced by the model by not very large variation of polarizability anisotropy parameters. In addition to that, a little drop from the experimental side. Diffuse scattering can be measured not only in single crystals, but we went further and did that in thin films. These films are of the thickness of 25 nanometers. It is very, very, very thin film. And still, using synchrotrons, it is possible to measure diffuse scattering in that. And temperature dependence is different, but the shape of diffuse scattering is similar, and it is consistent with what the model predicts. Then we go to this triangle from the scheme. Let's say, why does it happen? Can we understand why antiferroelectrics become antiferroelectrics or incommensurate? In other words, where from comes the minimum on the stiffness landscape? Basically, two questions. Why it first goes down and then it goes up? First, we answer why it goes down. There is a competition between lead sublattice and oxygen sublattice. Lead sublattice wants to have positive stiffness as ferroelectrics have. But the oxygen sublattice wants to have antiferrodistortive stiffness. And they are coupled. They are coupled by electric fields that they exert at each other. And if the polarizability of oxygen subsystem, the relevant components of that polarizability are large, then it overcomes the tendency to ferroelectric instability, and the initial stiffness dispersion is negative. And then why it becomes positive? Because the fields that cross-amplify the dipole patterns in lead and in oxygen sublattices, it diminishes on going towards the zone boundary. This is not due to the model, this is due to symmetry. So by simply analyzing the Coulomb terms, it is easy to understand why the predictions of the model are like they are. And this is some simple classification of perovskites with respect to their instabilities and diffuse scattering. This is a summary. On the right, it is a tolerance factor. On the left, it is the diffuse scattering character and the character of instability. And this, how it looks like within the model. How big is the polarizability? This requires some meditation, so I skip it and come to the summary. First thing is that this is the simplest way of calculating wave vector dependent Lorentz correction, but with accounting explicitly for the peculiarities of perovskite geometry in computing the Coulomb interactions. You cannot do it more simple. The next two distinctive stiffness landscapes are identified. And these landscapes are highly intuitive in the sense that what you expect from these crystals due to their crystal chemistry is actually what makes you the correct picture of the stiffness landscape. And then the competition between restoring short-range forces and destabilizing Coulomb forces is not only responsible for making ferroelectric instability, it can make also incommensurate instability or, for example, antiferroelectric instability if these incommensurate phases do lock in. So basically the explanation can be in principle as simple as that. And let's say it is intuitive that much that I tend to trust this view. It is very simple, but I think it might make sense. Thank you very much.
Okay, thank you. Okay, so while the next speaker comes up and gets set up, maybe we have time for a question or two? Yes? Rafi. It's as on as it's going to get. Oh, I thought people who would ask questions come to this mic. No, I don't want to run around it.
Okay, so why don't we see many incommensurate systems then? You know, we see a lot of ferroelectrics and antiferroelectrics and not really anything in between. Or maybe there are out there, I don't know.
Here the answer is because there is a small tolerance factor. Let's say oxygen overcomes ferroelectric instability. The tendency to antiferrodistortive instability overcomes the tendency to ferroelectric instability. This model gives this answer. And then there is a question why we have so many crystals with small tolerance factor.
But like, for example, I mean, one could vary pressure or some other parameter and maybe expect to see more incommensurate systems, but they tend to lock into ferroelectric or antiferroelectric.
That question makes sense because when we apply pressure, let's say incommensurate instability becomes enhanced. This is what we determine from the experiments. And also pressure should increase the tendency towards antiferrodistortive instability because tilts, they help to reduce the volume. So perhaps this makes sense. So this model can be sensible to describe pressure effects.
Okay. Well, let's thank Roman again.
Thank you.
Okay, and I'll introduce the next talk, which is Jirka Hlinka talking about cubic barium titanate dynamic displacement disorder. Thank you.
Thank you, Mr. Chairman, ladies, gentlemen, the organizers. Thank you to be here. Allow me to be here again. I'm going to continue to talk about Drosophilas of ferroelectrics, barium titanate. The subject of my talk will be this, diffuse scattering in the cubic barium titanate. And I think the reason for that is simply I think you have not yet seen this detailed diffuse scattering in cubic barium titanate before, and I think it could be useful. I think also in the context of many other problems discussed in this conference, like, for example, domain walls in barium titanate, it's important to know what kind of disorder we have in these materials. This is the team. Involves Marek Paschak from Department of the Electrics in Prague, Richard Welbery, Australia, Jiri Kulda from Grenoble, France, and Stefano Leoni, UK collaborator. All of them were very important in this work, which basically involves theory and experiments. So my talk I need to do a little bit of history to explain why we need new methods to go to the results, which involves diffuse scattering, but also, let's say, dynamics, which is behind of diffuse scattering and real space understanding of that. So history starts long time ago. So 70 years ago already, it was clear that It's titanium, or more or less clear that the titanium which goes off-center, as discussed by the previous speaker, in barium titanate. And if you think about the cubic phase, it should be the phase when the symmetry is restored. So on average, the position of the titanium is in the middle of the oxygen octahedra. But if we think not about Landau theory, but about statistical physics, we came easily in understanding that it's useful to think about titanium being somehow off-centered, and maybe there are some specific positions, which is the idea of eight-side disorder of titanium. And the real question is, or the real question was, because I think this question was clarified already quite a lot before, is that what's the dynamics? So how it goes in the cubic phase with this disorder? It's more like jumping from side to side between some distinct number of side positions, or it's more like rattling around the average mid position in the middle of the side. And 50 years ago, there was an important extra piece of information coming to that, and it was observation of diffuse scattering, and especially these lines, which are barely seen, but they were understood or very in detail already, and immediately after seeing them, that has to do something with the disorder of the titanium ions and the correlation between them. And originally explained in terms of phonons, but also in terms of eight-side model, and especially it was the observation in potassium niobate when the results were much more clear, the diffuse scattering was much stronger, and people have, this group, Gomez Lamborghini, they could see actually in different phases how these sheets of diffuse scattering are gradually disappearing, and the low temperature phase, rhombohedral one, they are not. So this piece of evidence seems to give a very intuitive and simple understanding of the phase diagram, the temperature phase diagram. Why we, in terms of configuration and entropy, it's very easy to understand that if we occupy 1 to the 8th side, there is no more diffuse scattering, no more disorder. There's some 50, I still stay 50 years ago, immediately there was some other understanding. This is the famous Wheeler paper, which tells us that this anisotropic correlation, anisotropic diffuse scattering, has something to do with harmonic interaction in the crystal, and has something to do with dispersion curves. And I think this is the first dispersion curves calculated in many different directions in the reciprocal space in 1995 by Henry Krakauer and coworkers in potassium niobate, showing that there is not just unstable mode at the gamma point, but in many other directions in the reciprocal space, but not all. So this explains this anisotropy. So that's more or less understood since a long time. Now, about the same time as the first principal calculations appeared, there was also a question, what happens if the unstable mode at high temperatures? And this is the simulations at finite temperatures, which show us the spectrum. This is at 11 times Tc, 3 times Tc, 1.5 Tc, and almost above Tc. What is the dynamical structure factor? This is the frequency and intensity, and we see the soft mode in barium titanate model, which is described by two-dimensional shed model at that time. And we see that originally one band, one soft mode, seems to develop as some complicated structure, like a new, what we would call central peak, and this central peak became extremely sharp at the phase transition. So actually, the original soft mode picture changed to the picture of all these order dynamics jumping between different sites in the model. And there is a first shell model calculation for potassium niobate showing something similar. Here, however, we don't see developing of the central mode. We see just one mode, which is broad, but softening down. And what was pointed here was that actually there is a whole branch of the mode, which is softening. But still, we don't see the central peak. And so the question is how it is in experiment. And so it was 10 years ago, it was possible to see actually some signature of the central peak in barium titanate, in the tetragonal phase. So in addition to the Slater mode, I mean the phonon frequency of the soft mode, there is a new excitation which corresponds to jumping between different sites. I illustrated here in more detail. So we are in tetragonal phase. So out of we can think about 8 minima around the center of the oxygen cage. 4 of them are occupied because we are in single domain tetragonal phase. But from time to time, we are oscillating the polarization, so it's oscillating up and down. But sometimes it goes to the position when there Whereas the other minimum, which is no more occupied, so more. So on average, it's a little bit occupied, actually, of the other 4 sites as well. So this is what we can see in simulations. Well, so the question is, actually, what happens in the cubic phase? So this was tetragonal. And whether it's somehow something special related to these diffuse scattering lines, because originally, or since long time, there was debate, if we have these diffuse scattering lines, are they related just to the soft modes, or is there something which more long-time dynamics or even static disorder which exists in the material? And okay, so that's our experiment. Experimental setup. The experiment was done at Argonne at the 11 IdB line with high energy X-rays, and the sample was somewhere here, so it was rotating so that we can collect the whole reciprocal space. Diffuse scattering, there is a amorphous silicon detector, and well, here are the results. So after some corrections and rescaling the calculated diffuse scattering into orthogonal coordinates, you can basically then make a cut in any direction in the reciprocal space you wish, and you really see nice these Gomez lines going through the principal breakpoints, and you can, for example, look for 1-1-1 plane, and you always still see this line. That's not all. We also try to do the same thing to calculate diffuse scattering from shell model calculations. For that, we have used the existing model parameterized by Tinte and Cepiarski some years ago already, which has the correct phase diagram. I don't think I need to discuss all the details. If you wish, I can tell you later how it's done. Okay, I can skip also the discussion. We tried this before, and we have found that the diffuse scattering could be well calculated in many perovskite materials. So the next step was to go to this one. And what's important there is that actually in these images, on the left side, you have experiment. The right side is the same diffuse scattering planes calculated by this shell model calculation. These shell model calculations. Now, maybe this works as well. Yeah, I'm sorry for forgetting about the microphone. At the first side, it's basically the same. So we have very nice description of the experiment by a model. And this has advantage that then we can look for real space configurations, the dynamics, and we can really dig in. So the calculation was done in 50 times 50 times 50 box. So we have we can make a cut through the simulating box, and each dot here, one of the 50 times 50, corresponds to 1 perovskite unit cell. And what is shown here is an instantaneous, it's not a snapshot of the configuration, and the color code displacement of titanium in the direction y, it's the vertical direction. So if you think about a small area, each dot is a perovskite lattice, so titanium, of course, is displayed in arbitrary direction, but we look how much only on the y component, and this is color-coded. Here is the same snapshot, but averaged over half a picosecond. So there is already some averaging, and here you can see there are stripes, which you can think about polar nanoregion or whatever, which are elongating along the y direction. So these are these longitudinal correlations, which were already understood 50 years ago. But what is important is if we do even longer averaging, let's say over 4 picoseconds, the intensity, the contrast fade out. So it means it's something which is short-lived. It exists over the time scale of picosecond. And you can even take one line like that and look in time, in longer time. The simulation was run over 100 picoseconds, but I showed just a piece of it. And you see that these clusters appear and disappear, appear and disappear. So they are more or less random. You don't see any area where it would stay for a longer time. So that's why when you average for longer than a few picoseconds, you lose the information about the cluster. Now we can do even more. We can look for the dynamic structure factor, which is intensity depending on the momentum transform and the energy, and it's, as usual, the double Fourier transform of the pairwise correlation functions. And we can look somewhere in the reciprocal phase, for example, along this line, what will be actually the contribution of different excitations to the diffuse scattering here. So if you wish, what is plotted here on this same line, on this line, we plot the frequency dependence of the excitations which contribute to the scattering of our X-ray beam. And we can do, so already you can see that these diffuse scattering lines, very sharp ones here and there, they correspond to a region when there is some excitations, which is very steep dispersion in this direction perpendicular to the line. We can do more. We can actually trace how the integrate the intensity part by part. For example, if you would integrate the intensity over first 10 milli-electron volt only, then you would mostly get contributions from these pieces, and you see that it has a peaks here and there, just in the position of the sharp lines. If, on the other hand, you would integrate between 10 and 20 milli-electron volts, you would integrate mostly this wave, this acoustic branch, actually the zone boundary, and this would give something which is much broader, and actually it's related to this intensity. And you can integrate everything as actually in the X-ray experiment. What we do the usual diffuse scattering experiment, and then you have the red curve, which corresponds more or less to the intensity measured in the diffuse scattering experiments. If I have time, I think I have time, I will just go along the line, along the diffuse scattering line. So that's where the intensity is strongest from that area. And then I get usual dispersion, which involve acoustic branch and optic branch. This is the last mode, the higher frequency mode, TO2 mode, if you wish. And the soft mode is here, it's the Slater mode, which is somehow for some trick making the higher contrast here. This is what you really measure, this is what we calculated. And this is done because we want to just look for the what's the spectrum at that point, for example, close to the zone center. And close to the zone center, you get this kind of spectrum. So this is from Slater mode to titanium motion. There is acoustic branch here, and there's the motion of the barium. And the characteristic frequency of that mode corresponds to one which is measured, let's say, in infrared or hyper-Raman spectroscopy. So we know that this mode is really the soft mode which describes the dielectric constant of cubic barium titanate. So I think with this diffuse scattering data and with this picture in hands and the model in hands, we can answer quite a few questions you might have about dynamical disorder in cubic barium titanate. So we have now this diffuse scattering documented for the barium titanate as well, not just for potassium niobate. We have model. We can look for the phonons, which are contributing to that. So we are basically doing in X-ray, computer the X-ray inelastic scattering. And we can see that the intensity which is here is coming from the phonons, and especially the COMET lines are coming from the overdamped modes, which have this kind of frequency dependence, and the frequency dependence match the dielectric spectrum, which we know to give the contribution to permittivity. So there is nothing below, nothing static. It's something which is time constant of typically of picosecond. We can also look then actually if you look for the position, let's say histogram of the displace of titanium, really in the cubic phase at that temperature, which is 100 Kelvin about TC, I forgot to say, there are 8 positions which are more probable, like most probable positions of the titanium. It's off-centered. But if you look how many of the titaniums are in these positions, only 5%. So 95% has energy which is over the barrier between them, so they are everywhere around. So most of the titaniums are just running around, so the barrier is very small. So the conclusion is that they are soft enough optic monons, steep enough to give lines, Q spectrum matches the electric one, and the conclusion there is no long-lived PNRs in cubic barium titanate. I mean the one which is the homogeneous bulk without defects. And so basically it is a displacive material with displacive cubic phase. That's my conclusion, acknowledgements, and a brief advertisement. Thank you for your attention.
Okay, so we have a couple minutes for questions. Please come to the microphones here if you'd like to ask a question. And yeah, the next speaker can come up as well. Yeah, go right ahead.
And also, I think it's I'd like to thank all my coworkers because it's demonstration that what we can do with the techniques nowadays.
But can I ask a question?
Yeah, please.
Yeah. The point is what it was long been believed that you have a coexistence of order, disorder, and displacive features. And this is what I don't see from your model or from your calculations to come out. Because as far as I can summarize the experimental situation, these two components which coexist are living on different time and length scales. And this is what I somehow miss in your approach.
Yeah, so our conclusion is that barium titanate in tetragonal phase has a clear distinction between lines, let's say, in time scale of the order disorder dynamics, which is jumping between the minima, and the, let's say, fluctuation of the order parameters, which are small fluctuations, the ones which are described in terms of phonons. But in the cubic phase, it's not the case. It's very hard, and I would even don't know at the moment how to distinguish between them. So there is only just one dynamics, at least at 100 Kelvin above TC. It's really something, but I think it remains even down to very TC. Everything can be described in terms of anharmonic phonon, one soft mount picture at any wave vector. And yeah, that's it. Yeah, so I would say it's order disorder material with displacive cubic phase.
To some extent, I agree on what you conclude. But for instance, if you look at the EPR and NMR data, then you clearly see that there is something like an order disorder component present above in the cubic phase, above TC. Yeah, this is the Blind's approach. You know that for sure.
Sure, I think he mentioned as much.
Well, just in a little bit in the same vein, we did similar simulations and went very, very close to TC. I mean, even barium titanate, of course, it's a first order, but you still have fluctuations. It's very interesting that if you're in the fluctuation interval, you get tweets, you get incommensurations and all that sort of thing, but it's only limited to an extremely small interval just above TC. So the general conclusion, I agree with you. But if you go into the fluctuation interval, then you have these additional excitations, which are quite strong, but limited to about 1 degree or 2 degrees.
Okay, I take it as a comment. I think for the sake of the time,
okay.
Maybe if you allow me to skip it.
As a service to the broader community, can you tell us briefly what dynamic disorder means? What's a reasonable definition of dynamic disorder that's different from thermal disorder?
Okay, so in principle, thermal disorder could be something which is extremely slow dynamics. I mean, the typical order disorder material is for example, phase transition in solid solutions of some ions which are diffusing, right? So that's, if I think about dynamic disorder, it was just a general keyword, but what I want to say that it can be described in terms of phonons.
Thank you. Okay, I understand.
And the number of the excitations is the same as the number of the harmonic phonons of the harmonic analysis of the material.
Okay, thank you. All right, let's thank Jirka again. Okay, and our next talk will be by Sergei Vakrushev, Mode Coupling and Modulated Structure in PZT as Seen with X-rays. Thank you. I'll tell you when you have 5 minutes left.
Yep. Okay, so I slightly changed the title of my talk, and I'll try to be fast, actually. So that's a list of collaborators, and I'll skip it. So what's the motivation? If we analyze the structure or the phase diagram of lead zirconate titanate, in the left-hand side, let's say, at the zirconium unreached part, we can identify, let's say, 6 order parameters. I should say we can identify 5 different type of superstructure peaks, and we do know that there is a softening of the mode at the zone center. So finally, it's ferroelectric. So the question is if we can find some general origin or general description for this. I should mention that we do discuss the lead-containing materials, and it is known that in most of the lead-containing perovskites, probably except lead titanate, the lead doesn't want to sit in, even above phase transition, it doesn't want to sit in its special 11000 position. But it wants to be shifted, and this shifts form kind of spherical layer. Inside this spherical layer, we can have complete disorder, and we can have different type of ordering. If you excuse me, do we have pointer? Yeah, so we can have indeed, it was discussed actually in a talk in a different way, but it was discussed in a talk of Roman Burkowski. So that's, we can have different type of, let's say, incommensurate or commensurate structures. Yeah. Okay, and some of them are known, like in PLZT, there is anti-ferroelectricity in lead zirconate. We can expect something like antiphase lead shifts in PZT. What we really can have in addition. So again, we all know about oxygen octahedral tilt that could be in phase or anti-phase. So, and finally, the picture that we can observe related to this oxygen octahedral tilts is rather complicated. And now we go to the pure lead zirconate first. At the first glance, it's more or less clear. At least we have our that was described in a paper explanation that looks consistent. Soft TO mode plus TA transition to at arbitrary Q, then unclub invariant anti-ferroelectric at exactly 1/4. Then Holokovsky order parameter coupling R order parameter. But in reality, even in the pure lead zirconate situation is more complicated, I'll show you. And in PZT, at few percent, or even in less than 1% of titanium, much more complicated structure pattern. So this is pure lead zirconate. So you see, this is high temperature, 473 K. In very narrow region, we do see M superstructure peak, 1/2, And if we go below, we do have indeed, again, we do have M superstructure and plus sigma superstructure. If you now look in slightly doped lead zirconate titanate, so let's have a look. So 0KL plane. In two different planes, we have slightly different picture, HK0 and 0KL. But indeed, what we have some complicated superstructure close to the zone boundary, close to M point. We do have sigma superstructure, anti-ferroelectric one. We have additional peak close to the close to this sigma point, which is kind of incommensurate or modulate structure. If we look on one-dimensional cut, which is much more easily seen, so look here. There is at 1.5 there are weak satellites. I'll show them more exactly later. There is incommensurate peak and there is anti-ferroelectric. So, do we indeed should we indeed consider that we have such a lot of different, let me call it, instabilities, or we can use more simple idea? So, actually, it was very long ago in a paper of Vitaly Ginzburg and Sobyanin, light scattering near phase transition. It was demonstrated, for instance, that if we have two modes, one of which is soft and other is not, and the one is temperature independent, the other one is soft. So at some moment when they want to intersect, the second one is becoming soft, and finally the result is condensation not of the soft mode, but of some other one, either the one that was not soft originally or some mixed. And then if you will go and consider just a simple picture of dynamical origin, classic mode softening picture, let's say, so it looks like this. The mode is just softens, but now let's consider that we do have acoustic on its way. Depending on the slope of acoustic, we can have two situations. If the acoustic is very low one, nothing happens. If the acoustic is rather high one, then they cross. And we do not expect any crossing for the modes that have same symmetry like it is in perovskites, where the optic and acoustic has the same symmetry at final Q. So I'll go the main idea of old paper of John X and Gian Sharana. So, and let's say that analyzing phonon spectra, we can expand phonon eigenvectors at any Q or arbitrary full orthonormal set. And in this case, first we will start to do it at Q equals 0. I'll go through the calculation. So what we can get if we expand it. So in reality, that's what we observed in a pure potassium tantalate. You see there is a soft mode, but we do have a strong change of the transverse acoustic. Now let's use this model and demonstrate how it should develop. There are two possibilities. Let's say that's exactly the parameters that were taken from the paper of X and Sharane. You see the mode at gamma point is softens and softens and softens. And finally, there is nothing because it's quantum paraelectric. Let's use the same parameters. And let me change actually the parameter F12 describing the mode coupling just 10%. You see, instead of a picture with expected phase transition at gamma point, we got the phase transition at some arbitrary Q. So that's indeed what can happen. And now to describe it later on from the point of view of scattering, we should now tell that we do not have, let's say, a real harmonic picture. We have kind of quasi-harmonic where we have a mixed term in our function. And then let's return to the lead zirconate titanate. So we are interested in this small region where there is very low concentration of lead titanate. And look here, the especially complicated picture we do see next to the M point. So we have many satellites of the first order, of the second order. The question is, what is the origin of these satellites? So there were several attempts to describe them as a result of some antiphase domains, but it doesn't work in details. So, but before going to the endpoint, let's have a look on SQ of omega plot, let's say measured with X-ray inelastic scattering. So we clearly do see something soft close to the gamma point. That's far away from the phase transition. We come more close. Here, we have now here the strong central peak, and we have something close to the endpoint. Now first to this part, to the low Q part. You see, not like in pure lead zirconate where we had just flat dispersion curve, we have some clearly, well, at least, if not the minimum, but at least the change of the slope at a final Q. And this change of the slope is probably the reason that it's not just in pure lead zirconate where due to the UMCLAP term, we create the first order phase transition with 1/4, 1/4, 0. But we have additional, as I told, we have additional incommensurate peak. But at the moment, I'm more interested in the zone boundary because nobody really even well, considered the zone boundary situation in details. As I told, we have complicated structure of superstructure peaks that couldn't be described by previously proposed picture of antiphase domains. So what we can do, in reality, we can consider that we have incommensurate structure described by two rays of the same wave vector star. And then, using the combination of these two rays, we can describe the satellites. Now, the main endpoint became the second order effect. And it's very reasonable because the total intensity of the satellites is much higher than the intensity of the than the intensity at endpoint. Now we can have second order satellites near the endpoint, and in reality we should have second order satellites near the major Bragg peaks, which we do indeed see. But now about possible origin of this. So it was excellent paper of Marek Pasiak that Irka was already referred to briefly, where it was demonstrated that close to the endpoint at some arbitrary temperature, I don't remember what it was, we do see some very strange, we don't see the peak at endpoint. We see some low intensity on one side and high intensity on the other. It was later demonstrated by molecular dynamic simulation that this peak could be simulated only if we can, if we take into account both, let's say, lead displacement and oxygen displacement. So that's the same, which is perfectly seen in lead zirconate titanate in PZT. In the, let me say, high symmetry, 0 minus 1515 peak, we have nothing. And here there is no contribution from the oxygen octahedral tilt. But if we do have contribution from the oxygen octahedral tilt, we do have some intensity, but that goes down not at goes up not at endpoint, but aside of it. So the question is still, in most, this is confirmed by S of Q omega measurement. Close to the phase transition, we do see the maximum on one side of endpoint, and we see nothing on the other side of endpoint. So what we can do? We know from first principle calculations that were published that we expect to have soft mode at endpoint exactly. How it can come into play? So the first question, if this endpoint, if this M3 mode can be coupled to the transverse acoustic, exactly at endpoint it couldn't be, but as soon as we moved slightly aside, it can be. It's shown here that the displacement of lead and titanium at the zone boundary now, when we move aside, has tau 3 component. The same is oxygen, that tau 5 is transformed to tau 3. So aside of the endpoint, we can have mode coupling. So now we use such very simple formulation, let's say, to look how the mode frequency could be renormalized. I forget at the moment about imaginary part of the coupling, just renormalization. So let's have a look of what can happen. To include renormalization, we consider that we have two modes, one with frequency at endpoint 2 millielectron volt, other is 6 millielectron volt, and we see that there is very weak coupling, very weak shifts of the position. But look here, what happened if the second mode goes down? It goes down, 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 and finally it easily can create the situation when we have the instability at final Q. Situation is very similar to that close to the gamma point. So we can try to follow the Funan line shape, but yeah. So it's interesting to look here. There is on one side, for instance, E2 is very high still intensity. On one side of the zone boundary, we have picture like this, the black one. On the other side, very similar. But finally, more close, you see already a large difference between frequency of one mode and the other one. We do see very strong change. So on one side, the intensity is rather low. On the other side, it's much higher. Finally, we do see huge central peak on one side, on of the endpoint and nearly nothing on the other side. And let's have a look how it change if we look now to S of Q omega. It's simulation. It's not modeling. No parameter. Let's say it's at least still adjusted. Just something arbitrary is taken to have something similar. We are far away from the, let's say, critical temperature. So we have nearly similar picture on left-hand side and right-hand side. So the frequency of the second mode, let's consider that this one is an oxygen octahedral tilt is going down, and the total scattering change, and now we have a situation very similar to I have shown you in the experimental picture. Yeah. Now let's have a look how the temperature evolution of the diffuse scattering integrated over energy should look. So it starts from some very weak peak on one side and minimum on the other side, and at some moment we have a situation. Situation very similar to what we observed and to what was described by Marek and Irka. So that's more or less possible description. Then, as I told, we can now consider that we indeed have two different. I already talked about this model. Two different incommensurate, we have incommensurate instability, then we have incommensurate phase transition, real phase transition, described by two wave vectors, and that's roughly it. And then I want just to show without any simulation, we are still working on it, so we did measurement on PZT20 with Peter Gerienko. More likely, Peter gave me possibility to participate in these measurements. So we followed the picture of inelastic scattering, neutron inelastic scattering in PZT20. If we will look now how the intensity map looks at final integrated signal, you see we do have kind of a peak on one side and next to nothing on the other. We are more close to the phase transition, strong peak in the inelastic scattering on one side. Elastic was excluded in this. It's energy integrated except for plus minus 0.25 milli-electron volt. And if we will look now on the dispersion, how it looks like this. We perfectly do see dispersion curve for acoustic going up. So some rising of quasi-elastic scattering here, and nothing on the other hand side. So that's situation very similar to what I have described. So I will skip this. And the summary is, I want to say that mode coupling is useful language for parameterization, because what I've been speaking is parameterization, not a theory. Anti-ferroelectric and incommensurate phase transition at Q around sigma point are related to the condensation of the mixed mode. Formation of these modes can be described as a result of mode coupling process. And complicated system of satellite peaks around 10 points is a result of incommensurate phase transition due to condensation of the mixed mode. The MCP structure is the second order. Thank you.
Okay, thank you very much. All right, we have a little time for questions, so please come to either of the microphones and ask.
So what would you say about the phase diagram then? Would you modify the phase diagram?
Well, I believe I once answered your question. It was in San Antonio. It was slightly previous version, so this one is modified. Well, it's there is kind of modification on the phase diagram in the sense that the intermediate phase is definitely not rhombohedral. So it's still ferroelectric, but it's definitely not rhombohedral. That's one point. The other one, we can see very narrow region of existence of kind of incommensurate phase with incommensurate wave vector of about 0.18, 0.180, something like this. That's kind of weak modification. So indeed, there is this ferroelectric phase. We actually confirmed it. We have a paper on piezoelectric force microscopy confirming that the phase is ferroelectric. But it is not rhombohedral. The fact that it's not rhombohedral is probably related to coexistence of kind of rhombohedral distortion at gamma point and plus this incommensurate close to the M point.
Will the next speaker come up? And in the meantime, I'll just ask a quick question. You've been describing these results in terms of mode coupling, but the previous speaker talked about dynamic disorder. Is there some relationship of these pictures?
Well, you know, dynamic disorder, I'm not sure that there is really something, let's say, well, you know, dynamic is already disordered because we just describe it in terms of phonons. So
Yes.
I try to follow the simple quasi-classical description in terms of phonon modes. So we can use whatever molecular dynamics will give you different picture to some extent. So I cannot tell if it is something in general or nothing.
Yes. Maybe what I was getting at is that mode coupling may be a pleasing description when it's a few modes, but when it's many modes, then it becomes too complicated to think this way.
Yeah, but I used very few modes.
Yes, I noticed. Yeah, exactly. Okay, so with that, let us thank Sergey for this interesting talk. Okay, and let's introduce the last talk of this session, Zhijun Zhu, probing short-range polar order in PZNPT and PMNPT relaxer ferroelectrics with neutron scattering. So I'll go like this to tell you 5 minutes left.
Okay. Thank you, the chairman and the organizers. It's my pleasure to be here to give this talk, and I come from NIST Center for Neutron Scattering and the University of Maryland. Let me first thank my collaborators here, Dr. Guangyong Xu and Peter Gehring, also from NCNR, and Chris Stock from University of Edinburgh, and Fei Li from Penn State. Thank you for the nice single crystal sample. And Sujun Zhang from University of Wollongong, and Zuo Guangye from Simon Fraser University. Our results are focused on two lead perovskite relaxer ferroelectrics, the PZN and the PMN, by doping with lead titanate, the PT. This system shows extraordinary piezoelectric and dielectric properties and make its considerable importance in technology. And the phase diagram of PZN XPT and PMN XPT are quite similar. At low temperature, the doping changed the rhombohedral structure to a monoclinic MPB phase, and in this talk we will focus on doping on the left side of the MPB phase. And one unique structure in this relaxer system is the polar nanoregion, PNRs here, which is first proposed by Burns and Deckholz in 1983. And this nanometer-sized local polar region appear at Burns temperature, TD, which is higher than TC. And the PNRs grows with cooling and persist into low temperature. Since the PNR are atomic deviation from their perfect position, so we can use diffuse scattering measure then by neutron or X-ray. Here is an example of measurement of PMN at 200K. Around 100 Bragg peak, we can see a butterfly-shaped diffuse intensity distribution extend along 110 and 1-10 direction. And around other Bragg peak, like 110 Bragg peak, there are just only one wing, but the intensity still distribute along 110 type directions. And in neutron diffuse scattering, the intensity are proportional to Q times epsilon, the atomic displacement square. So The red wing here, around 110 Bragg peak, should mainly come from local polarization along 110 direction. And the local polarization along 1-10 direction will contribute to diffuse scattering along 1-10 Bragg peak. And near 100 Bragg peak, they have contribution from both the red and the blue wings. Here are some our recent results in the PMN28PT single crystal, measured at 100K in the HKO plane. Around 100 Bragg peak, we can see clearly a butterfly-shaped diffuse scattering have both red and blue wing. And near 110 Bragg peak, mainly is from the red wing, but there are still some intensity from the blue wing, but much weaker. And near the 1-10 Bragg peak, it's similar, but on the opposite way. To better understanding the data, we also try to do a linear scan, which it's a K-scan at h equal to 1.1, which cross the diffuse scattering and avoid the strong Bragg peak. As we expected, for in zero field cool, the contribution from both red and blue wing should be equal or similar. And we see a symmetric two peak here. And from this scan direction, the left peak always from the red wing, and the right peak always from the blue wing. And near the 110 Bragg peak, we will see that the peak from red wing is much stronger, but still have some intensity from the blue wing. And near the 1-10 Bragg peak, the situation are similar, but on an opposite way. And also, we do some temperature dependence from 100 to 500 K. The intensity increase with cooling, but even at 500 K, which are above TC around 375 K, the diffuse scattering intensity is still there. And as we know, the diffuse scattering in the relaxer are easily affected by applying an external field. For example, in this case, we try to apply a 2 kilovolt per centimeter electric field along 110 direction. And then the diffuse scattering near 100 Bragg peak are clearly asymmetric now. The blue wing seems much stronger than the red wing here. And near the 110 Bragg peak, also the blue wing are much enhanced, and it's almost same intensity as the red wing here. And for the diffuse scattering near the 1-10 Bragg peak, the strong blue wing is even stronger and become dominant. And we just do some similar linear scan as before. And since we know that from the mesh scan, the electric field seems enhance the blue wing and suppress the red wing, and the intensity will look like this. For the scan near 100 Bragg peak, we see a clearly asymmetric two peak, and the right peak from the blue wing are clearly stronger than the peak from the red wing. And for the scan near 110 Bragg peak, the weak peak from blue wing are enhanced by the field, and at low temperature around 100 K, it's almost similar intensity compared to the peak from red wing. And near the 1-10 Bragg peak, the the strong blue wing is even stronger, which cross the top. And so here we have an idea that the 110 field will enhance the blue wing, which coming from the local polarization along 1-10 direction, and suppress the diffuse scattering coming from local polarization along 110 direction. And how about in other zone? For example, in the HOL plane, it similar have also polarization along 101 and 10-1 direction, and have the similar diffuse scattering pattern in zero field. By apply the same 110 direction electric field, the field could have no clearly effect compared to the zero field cool data. It's both the case around 110 bright peak and 1-10 bright peak. So it seems the 110 field have no effect on diffuse scattering coming from either the 101 polarization or the 10-1 polarization. And it's also the same case if we measure in the 0 KL plane. So the 110 field effect have no effect on this four kinds of local diffuse scattering from local polarization. And here are a summary of field effect in this system with different kind of field. And for here, we list 6 diffuse scattering associated with 6 different local polarization along 110 type direction. We just show the 110 field will suppress the diffuse scattering coming from 110 polarization and enhance the diffuse along from polarization along 1-10 direction, and have no effect on other 4. And we know the 111 field will enhance 3 kinds of diffuse scattering and suppress other 3. And the 001 field have no effect on either of the 6 type diffuse scattering. To understand this, we use a model we proposed before that at high temperature, the PNRs are almost random. By zero field cool, the ferroelectric domain is established along different 111 direction, and the 110 type polar nanoregion tend to align perpendicular to the 111 polarization of their surrounding ferroelectric domain. But if we field cool in a 111 field, the ferroelectric domain along 111 direction will become dominant, and it will enhance all 3 diffuse scattering coming from 110 type local polarization associated with this domain. Let's see how we use this model to explain our result. We have 4 different kinds of 111 ferroelectric domain, and each coupled to 3 local polarization perpendicular to them. And in the zero field cool, the population of each ferroelectric domain are almost similar, and so the contribution of each 110 type diffuse scattering are also similar. So they show average similar 6 different type diffuse scattering. And if we apply a field along 001 direction, it have no prefer on certain ferroelectric domain, and so the population will keep similar and nothing change. So the 001 field have no effect on either of the 6 110 type diffuse scattering. But if we apply a field cool in a 111 field, it have a preferred domain of the 111 domain and suppress other 3 domains. And it makes the 3 polarization associated with 111 domain enhanced and suppress other 3 kind of diffuse scattering coming from local polarization not associated 111 domain suppressed. And let's also see how is the field effect along 110 direction. For the 110 field, we'll prefer 2 domains along 111 and along 11-1, and don't like other 2 domains which perpendicular to the field. And in this case, the 1-1 diffuse scattering from 1-10 polarization will have 2 double source, will be enhanced, and the diffuse scattering from polarization along 110 direction have no source, will be suppressed. And all other 4 still have an average 1 contribution, and so it will be keep almost same. And here is the summary of my talk. The local 110 polarization tend to align perpendicular to the 111 polarization of the surrounding ferroelectric domain. And moderate field appear to mainly affect the macro ferroelectric domain itself, which have polarization along 111 direction, rather on the local polar order PNR directly. It's the end of my talk. Thank you for your attention.
Okay, this is very nice. And we do have a few minutes for questions, so please come up to the microphones. And while you're getting there, I'll sneak in a quick question. How rapidly does this change with composition, this picture that you have of the zero field cooling and the finite field cooling? If you change from 28% to 30% or to 25%, are they all extremely different or are they all similar?
General, on the left side of MBP phase, they are quite similar.
Yeah. I see. Okay. Anyone else have some questions? Maybe you're all ready for lunch. Okay, well, we really heard a lot of interesting new ideas this morning, so let's thank all the speakers.
Thank you.
This was very nice work. Thank you. Yeah. No, that's okay. So we have this recent paper about relaxer ferroelectric domains. Maybe we can analyze it in terms of 111 and 110 type polar nanoregions. I think it's a good idea. We only did zero field cooled. You know, we didn't really apply big fields. I'm glad to know about you. It's a very good work. Okay, I thought it was very enjoyable.
I work with Peter Guy.